This part of Lagos stands on land that did not exist here 2 decades ago. The Atlantic Ocean was here. Today, roads, underground utilities, construction sites, and high-rise buildings occupy a new piece of coastline extending outward from Victoria Island. But creating the land was only half the engineering problem. Engineers also needed a protected edge strong enough to resist waves, erosion, and overtopping along an exposed Atlantic coastline. That defense is known as the Great Wall of Lagos. Despite the name, it is not a giant vertical concrete wall. It is a massive armored sea revetment, made from rock and protected on the ocean side by enormous concrete armor units. Behind it, marine contractors used dredgers to place extraordinary quantities of material into what had previously been open water. The broader Eko Atlantic development has been estimated at roughly $6 billion or more. The project is privately funded by developer South Energy X Nigeria Limited, working in partnership with the Lagos state government and with federal support. And during major reclamation works, marine contractor DEME says more than 100 million cubic meters of material were used. But neither number explains the real engineering challenge, because before roads and towers could rise here, engineers first had to answer a much more basic question. How do you build a new coastline in the Atlantic and make it stable enough to support an entire city behind it? To understand why this project exists, you have to start with the coastline that came before it. A sandy beach may look permanent when you stand on it, but it is not fixed ground. Waves approach the shore at angles. They move sediment along the coast. Currents redistribute sand. Some sections gain material while others lose it. Over long periods, the shoreline can advance in one place and retreat somewhere else. Along the Lagos coast, that natural system had also been altered by major human infrastructure. At the entrance to Lagos Lagoon, 3 harbor moles built in the early 20th century interrupted the natural movement of sediment along the coast. Sand accumulated in some locations, while the shoreline farther down the coast experienced severe erosion. Waves, dredging, sea level change, and other coastal processes added further complexity. Bar Beach, beside Victoria Island, became one of the most visible examples. By the mid-2000s, severe erosion had dramatically reshaped parts of the shoreline. Project engineers have cited historical retreat rates of several meters per year in some sections, although those rates varied substantially by location and over time. That distinction matters. The engineering problem was not simply that ocean water occasionally crossed the beach. The beach itself was moving, and if the shoreline continues retreating, anything built too close to it can eventually become directly exposed to the sea. Eko Atlantic proposed a much larger intervention. Instead of only trying to preserve the old coastline, the project would extend usable land seaward and establish a hardened new coastal edge in front of it. The overall Eko Atlantic development is described at roughly 10 square kilometers, or close to 4 square miles, of reclaimed urban land. DEME says its own reclamation scope created about 9 square kilometers between 2009 and 2019. Those are different figures describing different scopes of the project, and the reclaimed land could not simply be placed in open water and left exposed. The protected edge and the new land had to advance as parts of the same marine construction system. The completed design for the Great Wall of Lagos calls for approximately 8.5 kilometers, or about 5.3 miles, of coastal defense. The current project site describes more than 6 kilometers of seawall in place. So, the planned full length should not be confused with the portion currently reported as built. But length alone does not explain why the structure works. The easiest way to understand this wall is to stop looking at it like a wall. It is closer to an artificial rocky coastline. From the Atlantic side, the defense slopes toward the sea rather than rising like a vertical dam. The concrete armor sits over graded layers of rock surrounding a massive rock core. Filter and geotextile elements help separate materials, while protection around the toe helps stabilize the base of the revetment against erosion near the seabed. Behind that structure lies the reclaimed ground. The Great Wall does not hold back a permanently higher body of water the way a dam holds back a reservoir. The water on one side is still simply the Atlantic Ocean. Instead, the revetment has to survive repeated wave attack. Its armor helps dissipate wave energy. Its rock mass helps resist movement. Its base has to remain stable as water moves across the seabed, and its crest has to limit damaging overtopping onto the reclaimed land behind it. That is why the outside of the structure looks so unusual. Much of the exposed ocean face uses concrete armor units known as Accropodes. Each unit weighs roughly 5 tons, or about 5.5 US tons. Their strange shape is deliberate. The armor layer is intentionally rough and porous. When waves reach it, water moves around and between the units, creating turbulence and dissipating part of the incoming energy. At the same time, the geometry of the units helps the armor layer resist displacement when they are correctly placed. The published project plan called for roughly 100,000 Accropodes, each weighing about 5 tons, across the full coastal defense. That does not mean 100,000 units have necessarily been installed already. It describes the scale of the planned armor system. The units are cast on site, then lifted and placed onto the prepared revetment slope. Project descriptions say their positions follow a predefined layout using GPS guidance. At ground level, a single unit is large enough to dwarf a worker. From the air, thousands of concrete forms merge into a rough gray surface, running along the edge of the Atlantic. But the wall only protects the edge. It does not create the land. For that, the project needed dredgers. One of the key types used in the reclamation works was the trailing suction hopper dredger. From the surface, it looks like a large ship, but in a typical dredging cycle, the vessel also functions as an excavation, transport, and material handling system. A suction pipe is lowered towards suitable material on the seabed. At its lower end, a draghead moves along the bottom. A mixture of sand and water enters the suction system and is pumped into the vessel's hopper. The dredger then transports the material toward the reclamation area. Depending on the operation, that material can be discharged or pumped toward the developing land. Then the dredger returns and repeats the cycle. One dredger can move a huge quantity of sand. Eko Atlantic required that cycle to be repeated at the scale of a coastline. DEME says more than 100 million cubic meters of material were used during its reclamation work. The significance of that number is not just the volume, it is the repetition. Dredge, transport, discharge, spread. Shape the reclamation front, then do it again, and again. As those cycles continue, open water becomes shallow fill. The shallow fill becomes a broad sand platform. And eventually, the new shoreline moves farther into the Atlantic. The city did not arrive on land. The land had to arrive first. But even that still does not produce a city. Freshly reclaimed material is not automatically a finished construction platform. The surface has to be shaped and graded. Drainage has to be established. Settlement and ground behavior have to be monitored and managed. Infrastructure corridors have to be created, and individual building sites still have to satisfy their own foundation requirements. The exact ground treatment approach can vary from one part of a reclamation project to another, so the important principle is broader than any single technique. Reclaimed sand is a platform. It is not a finished foundation. Once that platform becomes usable, the next engineering layer can appear. Roads divide the district into blocks. Drainage systems carry stormwater. Underground utility networks distribute services. Water, wastewater, and power infrastructure begin turning reclaimed ground into functioning urban land. Then, buildings rise above it. This is the point where the marine project can almost disappear from view. From a road inside the development, the ground may feel ordinary. The seawall may be far away. The dredgers may be gone, but the entire district still depends on what happened before the buildings arrived. And that becomes clearest if you look at the whole system as one continuous cross-section. Start underwater in front of the new coastline. The natural seabed lies below. Move towards shore, and the protected toe of the revetment appears. Above it rises the rock mass of the coastal defense. Across its ocean face sits the concrete armor. Cross the crest, and the wall stops looking like a separate structure. It becomes the outer edge of the land itself. Behind it lies an enormous mass of reclaimed material, occupying what was once Atlantic water. Continue inland, and that reclaimed platform becomes drainage corridors, underground utilities, roads, building sites, and eventually towers. At this point, the engineering logic becomes clear. The wall and the reclamation solve different problems. The dredging operation creates the land. The coastal defense creates the protected edge that helps keep that land in place. Without reclamation, there is no new urban district. Without a stable, protected frontage, the new land remains directly exposed to the same marine forces that reshaped this coastline before the project began. That is the central engineering achievement of Eko Atlantic. Engineers did not simply place buildings next to the Atlantic. They effectively moved the usable coastline outward and constructed a new armored boundary between the city and the sea. But fixing one section of shoreline in place does not stop the rest of the coast from moving. A coastline is part of a regional sediment system. Sand traveling along one section of shore can affect what happens farther away. Waves continue arriving, currents continue moving sediment, and when one frontage is hardened so that it can no longer retreat like a natural beach, the surrounding system has to adjust. A peer-reviewed coastal modeling study reached a more complicated conclusion about this effect. In its simulations, the Eko Atlantic revetment did not increase the total downstream erosion volume, but by holding the project frontage in place, it shifted some erosion pressure farther down the coast. The researchers therefore recommended continued monitoring and mitigation. That is a modeled long-term effect. It is not proof that Eko Atlantic alone explains every shoreline change observed farther east. The Lagos coast is influenced by many factors, including waves, sediment supply, harbor structures, dredging, sea level change, and other coastal development. But the study illustrates an important engineering principle. Protecting one frontage does not freeze the entire coastline. The wall may hold one section in place. The sediment system around it keeps moving. That means long-term observation is part of the project too. And Eko Atlantic itself is still developing. The reclaimed land is real. The coastal defense is real. Roads, infrastructure, and buildings are already present, but the full project is still taking shape. The current project site describes more than 6 kilometers of seawall, while the full planned coastal defense is approximately 8.5 kilometers. Urban construction also continues across the reclaimed district. So, Eko Atlantic is not one finished object. It is an evolving combination of coastal defense, land reclamation, infrastructure, and urban development. And that brings the story back to the image that makes this project so difficult to believe. The Atlantic Ocean was here. Today, part of a modern city occupies that space. But the most important engineering accomplishment was not simply moving enough sand to make water disappear from a map. It was creating a new boundary between land and ocean strong enough to resist the forces that had already reshaped the shoreline once before. Eko Atlantic shows that creating land from the sea is only half the engineering problem. The harder challenge is creating an edge strong enough to keep that land there, while the coastline around it never really stops moving.